Okay, so welcome along, ladies and gentlemen, to your weekly SETI seminar series. Today we're very lucky to be joined by Stephen Kane, who's come down to us from San Francisco State University. Stephen did a bachelor's at Macquarie University, bachelor's in science, and then did a PhD at the University of Tasmania in Australia, and then did a research fellowship at St Andrews in Scotland, and then came across to the United States to do a postdoc at the University of Florida. After that postdoc, he joined JPL, where he was at the NASA Exoplanet Science Institute as a research scientist, and he has just recently moved up to San Francisco State University. And his interests are in extrasolar planets and extrasolar planet statistics, using microlensing, transits, and radial velocity techniques. He's also interested in stellar and galactic kinematics, variable stars, and the outer solar system. He's currently PI of a search for more exoplanets using WASP-0 and in the Super WASP consortium. And he's the PI of a project called TERMS, which is being used to refine transit ephemerides for transiting exoplanets. Today he's going to talk to us about habitable zones and the exoplanets that may or may not occupy them. So please join me in welcoming Stephen.
Well, thank you very, oh gosh, I need to keep my voice down. Thank you very much, everyone, for your patience with the technical difficulties. I hope to make it particularly entertaining to make up for that. So this is a talk I'm giving as somewhat of a public service announcement. I want to talk a little bit about the Habitable Zone, what we know about the Habitable Zone, what the Habitable Zone is, and what it isn't. And I should warn you ahead of time that this talk is going to sound a little bit depressing. It's going to sound awfully cynical, but I will make up for it because I'll have some new results that I haven't shown anyone outside this room before. And at the end, I'll put a positive spin on it all, and hopefully you'll all leave the room a little more upbeat. So first of all, to tell you a little bit about myself, I have been working on exoplanets since 1996, and that's when the whole field really exploded in an extraordinary way. So one of the most difficult questions I get asked, though, is what do you research, or even what are you working on lately? Is difficult for me. Well, when I'm not saving aliens and returning them to the mothership, I'm working on a variety of things. I've had about 150 refereed publications, 40 as first author, and when you look at my publication list, it's very difficult actually to pin down what it is actually that I do, and that is because I've had the great fortune of working on a variety of topics. As you see here, I started in 1996, and since then I've been working on microlensing, transits, radial velocities, now working on imaging detection methods as well, orbital stability, and then a lot of these things came together over the last couple of years to get me interested in the topic of habitable zones and habitability. Now, the topic of habitability is of great interest, no doubt. In fact, when people think about planets, one of the first things they think about is life. And to give you an example of that, one of the first exoplanet discoveries I was involved with was one of the transit planet discoveries from the Super WASP mission. And I remember during the press conference, this is back when hot Jupiters were still ironically cool, and we could have a press conference about a hot Jupiter. And despite explaining to the press that this planet had an estimated surface temperature at the top of the atmosphere of about 3,000 degrees Kelvin, was in this 4-day orbit around its star, one of the press asked, do you think there could be life on it? The thirst for looking for planets with life on them and understanding what that frequency is, it's insatiable. It's insatiable. And so this is something that is good. It's very good, but it's something that we also have to be very careful with, and that's going to be somewhat of the theme of this talk. And another example, earlier this year, a couple of months ago, for example, there was the announcement of water under the surface of one of Saturn's moons, Enceladus. And so this raised all the questions, the usual questions about life. Astronomers have been searching for planets that might be able to support life for years, clearly indicating that us exoplanet hunters need to raise our game a little bit because we're finding it apparently in our own solar system. Why? Because there's water. I'll come back to that in a moment. But this topic of looking for life elsewhere can get a little bit crazy. You have very strange stuff which is written about, for example, not just life, but unlife, zombies on other planets. There was this insane article which was published early this year, around about the same time the Enceladus result came out. And it was a study, it was written by Stephen Kane. I guess I have some explaining to do. All right, so let me explain. My colleague, Frank Celsus, and I were very intrigued by the whole search for biosignatures around other planets, and so we wanted to take it one step further and postulate that since zombies are so popular in current culture, that even though we haven't seen a case of zombieism here on Earth, it must have happened somewhere else. And so we conducted a thought experiment. What if everything on the surface of the Earth, the biomass, died and you returned it to the atmosphere? Could you detect that signature? We called it a necrosignature. And we did in fact write a paper about it with just enough science in there to make it seem a little bit plausible. And the beauty of it is that it also helps to explain the Fermi paradox, because all civilizations are at some point succumbing to a zombie apocalypse, and that's why we haven't encountered anybody yet. But despite the fact that, given aside the topic of the study and the fact that if you translate Chateau Morts Vivants, that translates to Castle Undeath, and that it was submitted for publication in the Necronomicon, and that it was published on April 1st, there were physics forums which took this paper seriously. And it was, I just stood back and let the circus unfold. It's ironic to say that the paper took on a life of its own. So it was an interesting study. But going back to water, one of the major things that we're trying to do, it's often said that what we're trying to do is follow the water. In fact, some people say that wherever we see water on Earth, we find life. Not a watertight argument on its own, because of course the Earth has been contaminated for 4 billion years. Of course, wherever we find anything on Earth, we find life. The life has burrowed deep into the Earth's crust after 4 billion. This is why we need to spend so much effort trying to decontaminate everything we send to Mars. It's actually a really difficult thing to do, to remove the life from something which has been on the Earth. But water does have a couple of redeeming qualities, and that is, it is a natural solvent in which biochemical reactions can take place. We do know that it has played a major role for life on the Earth. And of course, it is extremely common. Water and oxygen, some of the bioessential elements, some of the most common elements in the universe. Water is extremely common. We're discovering that in our own solar system, for example, Enceladus. And so water is a natural place to think about when we're thinking about life. And so this has caused people to start thinking about, okay, so where could we find water elsewhere? And in case you think that the habitable zone is a recent invention of the Kepler mission, for example, to publicize their discovery. People have been thinking about this for decades. This is just one example, one of the earliest examples you find in the literature, not too far from here. Someone at Berkeley was thinking about this in 1959, and they published this in PASP. And here they're saying, let's reconsider the Habitable Zone around a star. And it was one of the first attempts to quantify that region around a star where you could have liquid water. But the habitable zone. The habitable zone is, like my zombie paper, taking on a life of its own. It's starting to mean different things to different people. This is something that some of you may have seen doing the rounds on Facebook a little while ago about different perspectives on the same situation. What your friends think you do, what your mum thinks you do, and so on and so on if you're an astronomer, whereas what we all actually do is program in Fortran 77. Just me then. Okay, so when it comes to the habitable zone, I could go to, not just to the public, mind you, I could go to an astronomy meeting and ask 5 different people what they think the habitable zone is and get 5 different answers. And it's becoming something which is actually fairly damaging to the field. And I'll show you why. First of all, let's look at what the media think that we mean. When we talk to the media and we talk about the habitable zone, the name itself, of course, is a little misleading. But when we talk to the media, and the media, you see a lot of the press releases that are made about planets which are in the habitable zone, then they can easily, and the public, be conjuring up pictures of lush landscapes. Depending on the press release you see, it can even get a little bit divergent. You think I'm joking? I've seen astronomers suggest that this is what's going on planets which are in the habitable zone. And so this is something which can be very misleading. Now, astronomers, as I said, themselves have different ideas of what the habitable zone is, and an astronomer could be forgiven for thinking that when we talk about a planet in the habitable zone, we're talking about something which at the very least has liquid water on the surface and looks something like that. However, I've been at astronomy meetings where I will overhear a conversation. I don't go out of my way to do this, by the way, but I overhear conversations where 2 astronomers are talking to each other, and one of them will be saying to the other, you know, I think the phrase habitable zone, the whole concept of the habitable zone, is garbage. It's rubbish. There's absolutely no way we know if those planets are habitable. And of course, they're absolutely right. So what's happened? There's been a disconnect in information somewhere. So let's talk about what the habitable zone really means. The way in which the habitable zone is defined is the region around a star where water could exist in a liquid state on the surface of the planet if it has sufficient atmospheric pressure. So there's a could and an if in there, already mirroring the uncertainty involved. Now, a couple things that it isn't. The habitable zone is not telling you that there's water on the surface. It is not. There is different ways in which water can be delivered. We kind of understand that for our solar system, how water was delivered to the terrestrial planets. May not happen the same elsewhere, and so we don't even know if water's there in the first place. It certainly is not commenting on habitability. It is certainly not commenting on the presence of life, and so we need to be very clear about that. And of course, the anthropic viewpoint of all of this is that we're basing this on one single data point, and that's us. And if you give me a single data point, I will fit to you whatever curve you want. But we need to keep that in mind. So what is the habitable zone? The habitable zone is primarily one thing. It is target selection. Even though we don't know anything about what's going on these planets which are in the habitable zone, we do know that this is a good place to start looking. And so what the planets in the habitable zone are for, they are for target selection for people 20 years from now. And I'll talk more about that in a moment. So we need to be very careful about our terminology because this is something which is often mixed up. And if you just change a word here and there, then you can completely change the meaning of what it is that you're talking about. And press releases which talk about habitable planets, or that the galaxy is filled with habitable planets, they do a disservice to the public, they do a disservice to the scientists who are working on the field, because they're misrepresenting what it is that we actually know. And so there is no viable catalogue of habitable exoplanets, because we don't know of any habitable exoplanets. That number currently stands at 0. So I'm going to leave you all with 5 points from this talk, and to be completely clear about my first point here, I like Christmas. I like opening my Christmas presents early as much as the next person. But when we try and scoop the discoveries from 20 years from now, let me tell you what's going to happen 20 years from now. 20 years from now, maybe we will get a low signal to noise detection of an atmospheric constituent in a planet the size of the Earth. Will that be unambiguous? Of course it won't. The scientists will debate for years as to what that actually means, whether there are geological processes which could have produced the same thing. That's what's going to happen. The good news is that there are some very clever people who are working on that problem, people like Sarah Seeger, Vicky Meadows, Sean Dumgarl Goldman, who are trying to create a matrix of unambiguous biosignatures. But when we get there, and this is before we've even looked at the surface of what's going on at the surface of the planet. So we do ourselves a disservice by trying to attempt to scoop the discoveries which are going to occur decades from now. And it's very tempting, because all of a sudden we have all these Earth-sized planets, we have something called the Habitable Zone, and we put 2 and 2 together and get 7. But we need to be very careful about doing that. So point number 1, we have not discovered any habitable planets, and don't let anybody tell you otherwise. So, now that I've gotten you a little bit depressed, let's see how much deeper I can go. The Habitable Zone, I make it sound actually a little bit simpler than it is. I've already given you this definition of that's where the liquid water could be if it has sufficient atmospheric pressure. But there are different models which are used to calculate where this region really is. And there's a sample of those papers here. I'm not going to go through each of them in detail. Some of them are based on the Earth, some of them are based on a kind of a dune planet, where you could have a period of time where it hasn't gone into runaway greenhouse, but it doesn't have any liquid water on the surface, and so at least the temperatures are okay. So these affect the boundaries of the Habitable Zone, all these different ideas. What I'm going to be using mostly throughout the rest of the talk, full disclosure, is these last couple here by Koparapu and Jim Casting's group, which use these one-dimensional and three-dimensional climate models based on the Earth. So a graphical representation of that looks like this. And I really, really like this plot for a couple of reasons. One is that you can see on the y-axis, it's showing the dependence of the Habitable Zone boundaries on the temperature of the star, different for different types of stars. Why? Not just because there's a different, bluer stars are brighter, obviously, but red stars have more infrared flux. Greater percentage of their total flux is in the infrared wavelengths. And that's very important for calculating the effect of greenhouse and so on the surface of the planet. On the y-axis, if you weren't paying attention to the axis, you might think, shouldn't that be separation? But it isn't. It's the amount of stellar flux which is incident on the planet. And so on here, I've got plotted various examples of real exoplanets which have been discovered. And you can see that some of them fall within the boundaries. There's a couple of different boundaries you can think about. One is, for example, the runaway greenhouse. Runaway greenhouse sounds ominous, and it is. It's kind of what we like to think about where an Earth might turn into a Venus. But there is another more optimistic boundary called the recent Venus, which is the idea that Venus could have had liquid water on its surface up until about at least a gig-a-year ago. So there's different scenarios, since we don't know exactly the full history of the Earth and Venus, that we can consider. And similarly with the outermost boundaries. And so we tend to think about conservative habitable zone and an optimistic habitable zone which stretches it out a little bit further. Now, there have been quite a few discoveries of planets in the habitable zone over the years. And this is a graph I made which shows the discovery rate. So on the x-axis you can see the year of discovery. Now the different colors are showing the red is if the planet is interior to the habitable zone, very hot, and the blue is if it's exterior to the habitable zone. And the green are the ones where at least 50% of the orbit is within the habitable zone. Why 50%? Because some of the planets are in eccentric orbits. So some of them are not spending all their time in the habitable zone. They kind of swing in and they swing out again. So you can see we've been discovering planets in the habitable zone for many years. Well, so what's the big deal then? So the big deal, of course, is that all these earlier planet discoveries, they're all Jupiters. Jupiters in the habitable zone maybe have habitable moons, who knows? The discoveries from the last couple of years have been dominated by Kepler. So these ones here, where you see the 14, the 4, the 10, and the 9, those are discoveries from the Kepler mission. And those are more interesting because they're more likely to be terrestrial. And so those are some of the interesting ones that we've been discovering lately. Now I'm going to try and switch to, oh, here we go. So this is one example of a planet in the habitable zone. Elisa Quintana and Tom Barclay and Jason Rowe are sitting right over there, and so they were the lead authors on this discovery. So this is an animation using actual made-up footage of the planets orbiting the star in the habitable zone, and then we zoom in on the 5th planet of this system, and we can see that it looks remarkably like the Earth, except with larger ice caps, because it's actually towards the outer edge of the habitable zone. Now, one of the interesting things about this planet is that, and I think Elisa is actually going to come here in a few weeks herself and talk about this, is that this planetary system is around an M-dwarf. And M-dwarfs have their own characteristics which are quite distinct from the Sun. Things like that they tend to be more active, and they tend to be very spotted, and the planets tend to be closer, to the star, and so they're more likely to be tidally locked, for example. So that's one example of one of the more recent planets in the habitable zone. But what about the habitable zone boundaries? Well, let me just tell you a little dirty secret about habitable zones. And that is, habitable zones is one of those areas where 99% of scientists make the rookie mistake of not considering the uncertainties, the error bars. The boundaries of the habitable zone depend upon the properties of the star, most particularly the luminosity and the effective temperature of the star. And those have uncertainties, sometimes quite significant uncertainties. And so what I'm showing here is, on the top I have effective temperature and the sigma effective temperature, the uncertainty. And at the bottom I have the stellar radius and uncertainty on stellar radius. So I'm showing the distribution of it. And this is for the Kepler candidates. So what we can see is that for the effective temperature is something that you can normally measure pretty well. Even if you have a color, you can get a pretty good idea of the effective temperature. Luminosity, on the other hand, is a little more difficult because you need to know the radius. And the radius of stars is very, very difficult to determine, at least with any reasonable accuracy. And if you're just using colors to determine things like the stellar radius, then a lot of the time you'll be substantially incorrect. So what this is showing down the bottom is the stellar radius distribution. You can see it peaks around one solar radius. So a lot of them are like the Sun, we think. But the uncertainty, you can see, is actually a very large fraction, peaks around a very large fraction of the stellar radius that we assume it to have. So what does this mean when we take these uncertainties and propagate it through into our estimate of where the habitable zone boundaries are? We get something that looks like this. So what this means is that if you had perfect uncertainties, you knew exactly how big your star was and how hot it was, then you'd be right here at 100%. The habitable zone is where you think it is. But as the uncertainties increase, this increases to 200%. What that means is that if the habitable zone uncertainty region at 200% means the boundaries could be in a region twice as big as you think. And if you go up to 300% and so on, and you can see that's near where it peaks, which means that for a lot of the Kepler candidates at least, we don't always really know what we're looking at. And sometimes we look at something which is a habitable zone candidate, and then it goes away because we don't really understand what the properties of the star are. It's something which is a significant problem, and something that we're trying to grapple with a lot of the Kepler candidates. All right, so the main point of Kepler, though, of course, is to determine something which is called eta Earth. Eta Earth is also something which, if you ask 5 different astronomers, you'll get 5 different answers. But broadly speaking, eta Earth is the fraction of stars with at least one terrestrial planet within the habitable zone. So that's what Kepler was designed to do. We're trying to find the planets which are in the habitable zone. And there have been a few different people at this point. There is more than enough data now from Kepler to actually try and determine what this quantity is. And there are a few people who have tried different methods using different habitable zone boundaries and so on to determine what this is. For example, you have eta Earth values of 15% of stars have a terrestrial planet in the habitable zone. Ravi Koparapu would beg to differ and say that the answer is more like 50%. And that's just for M stars. If you look at different spectral types, you'll find different numbers. The occurrence of planets is going to vary with the type of the star. So there was a result from Pettigrew et al., which gave a number of 22% for sun-like stars. But here's the thing, of course, is that Kepler is using the transit method. And depending on how much you know about the transit method relies on the planet orbit crossing our line of sight. And so there's a probability associated with that, which is extraordinarily biased towards shorter periods. So Kepler is biased towards detecting the transiting planets at shorter orbital periods. So years from now, like I said, the habitable zone is about target selection. And so let's go forward in time, 20 years, 30 years, however long it takes for us to be able to take a picture of one of our candidates from the habitable zone, and I actually have a picture of an Earth-sized planet around a sun-like star. That was supposed to look like Earth. That's what they'll be saying 30 years from now when they take a picture. That was supposed to look like Earth. Now, this is something that I often say, and that is all conversations regarding habitability are worthless if we ignore the limited data we have in our own solar system. I go to a lot of astrobiology meetings now, and I get to interact with planetary scientists, and I discovered something interesting. I discovered that planetary scientists make jokes about exoplanet people. They do. They make fun of them. So any exoplanet people here or watching on YouTube, the planetary scientists people are making fun of you, and they're saying this. They're saying the exoplanet people are only just now discovering that there are planets in our own solar system. That's what they say about exoplanet people. And they've got a point. I mean, the planetary scientists have been analyzing the properties of planets in our own solar system for years, for decades, centuries. And exoplanet folks are now discovering analogs of things which are in our own solar system as though it's revolutionary. So that's, I can understand where they're coming from. But this is something which we need to be careful about when we're talking about the habitable zone. Whenever we have something which is the size of the Earth, our temptation is to always just compare it to the Earth, ignoring that we have a sister planet, which is 95% the size of the Earth. So one example of this was Kepler 69. Kepler 69 is a fantastic system. Tom was the first author on that. And it's a two-planet system where you had an inner planet in a 13-day orbit, and then you had an outer planet, which is in a 240-so-day orbit. And when we looked at the planetary orbits and the habitable zone, what we actually found was that something very interesting, and that is that planet receives 1.9 times the solar constant. If that doesn't sound familiar to you, that's exactly what Venus receives. Exactly what Venus receives. And it's in a slightly eccentric orbit, as far as we can tell. So you can see it kind of skirts the inner edge of the optimistic habitable zone and then goes back in. And so Tom and I wrote a follow-up paper about that, describing it as a super Venus. But there's still plenty of media articles online that refer to this and have wonderful pictures of it as a lush Earth-like planet. But it was very interesting to see examples like this. And this is something which I've been very interested in because I'm very interested in the dichotomy that we see in our own solar system. Let me just pause and say that I realize using the word dichotomy when you have exactly two objects in your sample is ludicrous, but they are very different from each other, in fairness. And so I'm very interested in Venus, Earth, the divergence of their atmospheric histories. So, a more interesting question may be, well, forget about E to Earth, what's E to Venus? I mean, there's maybe a lot of Venuses out there, and as I mentioned earlier, Kepler is biased towards the shorter period planets. That means that Kepler is far more efficient at telling us about Venuses than about Earth. So what we can do is we can re-look at the Kepler sample and define this region which I'm just going to call a Venus zone, just because runaway greenhouse doesn't roll off the tongue as well. But the Venus zone stretches from the runaway greenhouse boundary of the habitable zone all the way in to a boundary that you can calculate based on atmospheric erosion, where a terrestrial planet will lose its atmosphere. And then you find that the unsurprising result, actually, that the values for E to Venus are not too dissimilar from E to Earth, but with significantly smaller uncertainties because you have more objects in your sample. And so that's something that Kepler is teaching as well about the prospect that there are actually a lot of Venus analogs out there. So point number 3, Kepler is discovering the Venus analogs first, and that is the planets which may possibly be like Venus. Now, an interesting part of this whole exoplanet adventure has been, from 1996 when I first started working on this, has been the progressively more sensitive experiments going down and down in size and down and down, mostly in mass, but now with Kepler with size. And so as you dig deeper, you discover, it turns out, a lot more planets, but also a greater diversity. And so far I've been talking about Earth-sized planets, Venus-sized planets. But, of course, we now know that there's a continuum. There's a continuum of sizes that stretches all the way from bigger than Jupiter all the way down, down below the size of Mars. So some people have tried to put the mass and radius together to try and understand the mass-radius relationship of exoplanets. Now, with the giant planets, it's actually a little easier to understand because giant planets tend to be more governed by things like hydrostatic equilibrium and so forth. And so when you look at the giant planets, which are over here in this diagram by Lauren Weiss, who's looked at this a great deal, then you can make a little sense out of that and actually come up with a reasonable mass-radius relationship. Once you start dumpster diving down into the terrestrial regime, you discover, well, for one thing, your uncertainties go up because we can't measure them as well, but the diversity also increases. And so there's this interesting relationship with the exoplanets, the mass radius, as you go down to the smaller sizes. Now, when we look at a plot like this is one of the plots from Kepler showing their discoveries, absolutely extraordinary. And what they tend to do is they use these units of measurement. Lots of people in exoplanets do, units of measurement. An Earth, a Neptune, and a Jupiter. Very, very convenient. What isn't convenient is that our solar system seems to have missed out. It's weird, because I mentioned that there's a continuum of objects. In our solar system, the largest terrestrial planet is Earth. To go to the next size, you have to go to Neptune, which is about 4 times the size of the Earth. And so we're missing a planet around about 2 Earth radii. It could have been there. In fact, I had read about this. There was this interesting search for this planet, this hypothetical planet called Phaeton. I don't know if any of you have read about that. It's quite interesting because when the asteroid belt was first discovered, there was very quickly put forward the idea that, oh, this is the remains of a planet that was there but then blew up or something like that. And so we should have had a Phaeton, except, of course, probably it was Jupiter's fault. It's your fault that we don't have this because it was disrupting planet formation in that region, because that's where a lot of the orbital resonances are, we know, in the asteroid belt. The trouble with this is that it becomes an interesting psychological experiment because we've got nothing to compare to now. And so when we look at things like tables like this, or we look at just numbers of something which is 2 Earth radii, we can look at it and think, it's bigger than the Earth, but at least it's not Neptune. Therefore, I say it's habitable. Something like that. We don't have a Phaeton to say, oh, this is 1 Phaeton radius. Instead, we end up coming up with ridiculous terms like super Earth or mini Neptune. And we're missing something there. We're missing this diversity in our own solar system. It's actually a real problem. When you put the two side by side, okay, so here's Earth with our missing Phaeton. And when you put them side by side, and that radius translates into volume, it translates into extra atmosphere, a substantially larger mass. 2 Earth radii probably means something like 7 or 8 Earth mass. Then you know that they're not really like each other at all. It turns out that there is seems to be some kind of transition which occurs at around about 1.5 Earth radii, and there have been a few people who've written about this now. 1.5 Earth radii was something will start to transition from a terrestrial planet to a giant planet because it reaches a certain mass, starts accumulating a lot of gaseous material from the envelope, develops a substantial gaseous atmosphere, and that's where you see it transitioning into more like a Neptune. So that does seem to be becoming a little bit clearer. There is a diversity there, so there are always exceptions to the rule. But point number 4 is, of course, that don't ever let yourself be fooled into looking at these press releases and saying, we've found a super Earth in the habitable zone. Great. So what does that mean for Earth? Because we know that they're not the same. And so we can't be fooled by the psychological experiment just because we're missing it. That means we'll round it down to be like the Earth. Okay, so my final little quandary with habitable zones I wanted to bring up was the issue of circumbinary habitable zones. This has been a very, very interesting one because we've seen it in science fiction. We presume that they were very, very difficult to detect. And they are difficult to detect, but we underestimated how common they were, and that is circumbinary planets. So there have been a few people who've written about this. There have been a few people who've written about the habitable zones of circumbinary systems, myself included and several others, and it becomes something which becomes rapidly very complicated. And if I just show you a schematic of why that is, what we have, of course, is our two binary components in the center of the system. These tend to be relatively short period, and when I say short period, I mean 10 days or less, something like that. So we have these two different stars, different insulations, and then we have a planet which is on a Keplerian orbit, usually, and then we have this stability region because it can't come closer than that to the center of mass of the binary and still be in a stable orbit. Then we put everything in motion. The binary is orbiting, the planet is orbiting the star, and the insulation received by the planet is going up and down all over the place. And it becomes something which becomes rapidly very complicated. So what you end up with is a time-dependent habitable zone. A time-dependent habitable zone with a planet in a Keplerian orbit moving through it. So it's not very simple. So I'm going to skip to point 5 here, which is something that I went great pains to try and discover, which is that the habitable zones of circumbinary systems are extremely complicated. And when I published that paper, beginning of 2013, I was contacted by a member of the press from New Scientist. And what I found with the press, I mean, you have some members of the press who want literally 2 minutes of your time and they're done. But then you have other ones who want to talk to you for an hour or so. And if you do that, then just be careful that you just get so relaxed that you'll say anything, because the press want to get you at that moment where you say something controversial. And so at the end of an hour of talking to this person, I felt I'd given layman answers to the questions, and it was all very good. And then she hit me at the end with the question I wasn't expecting, which is, do you think Tatooine from Star Wars is habitable? Yes or no? I was feeling a little bit cynical, like usual, actually. And but I had been thinking about it earlier that day, and I had looked at this picture of Luke looking at the twin suns of Tatooine, and I looked at the angular separation of those two stars on the sky is a minimum angular separation. They could be further apart, and you don't know what point in the orbit you're looking at. But then you can look at the size of the stars and do some rough back-of-the-envelope calculations. And so what I ended up saying was, if one were to calculate the boundaries for the Tatooine system based on film footage, there's a very real possibility the planetary system, as depicted, is unphysical. This would not be a big surprise since the film was produced far before any of this kind of research took place. The amount of hate mail I got from Star Wars fans was unbelievable. I was shocked. And Ravi Koprapu, who's written several of the papers I've mentioned so far, he is a Star Trek. You know about the true dichotomy of Star Wars and Star Trek. Well, he's in that camp. And because he knows that I'm not in that camp, he assumed I was Star Wars. And he said to me, that must have really hurt to say that about Star Wars. And I said, well, actually, I hate all science fiction, so it was actually no big deal. But I did learn that, as well as politics and religion, Star Wars and Star Trek are off the table as well. Right, so now I want to bring it home with a little less cynicism than I've been showing consistently through this talk. And so the 5 points I've made is that we have not discovered any habitable planets. The habitable zone boundaries are uncertain. We need to understand the properties of the stars. That Kepler is discovering the Venus analogues first, and that super Earth is definitely not the same as an Earth, and that the habitable zones of circumbinary systems are complicated. But there is good news. The good news is that, as I said, the habitable zone is target selection. And JWST is going to have a lot of work to do, no shortage, especially with TESS coming up on the heels of Kepler. There's going to be a lot of work to be done. So there's a lot of target selection there. Now, with regards to the second point, yes, the habitable zone boundaries are uncertain, but that just motivates us to understand the properties of the stars better. And understanding the properties of Kepler stars is an ongoing effort. This guy by the name of Daniel Huber in particular, I've pointed out there, who's done some great work in publishing new results that greatly refine the properties of the Kepler stars. For number 3, Venus analogues, in case I haven't made it clear so far, I find the whole concept of discovering how common Venus-like planets are actually very interesting. And so even though Kepler is far more efficient at finding our sister planet than finding ours, to me, actually, that's pretty interesting. And understanding the divergence of Venus and Earth, I think, is going to be one of the major undertakings in future years as we discover more of these kinds of planets. Super-Earth is not equal to an Earth, but on the other hand, super-Earths appear to be very common. Like I said, we're very strange that we don't have one. And so understanding the super-Earths more and more is going to become a very interesting topic just because there's so many out there. And so it's going to be great to see that research go forward. And finally, circumbinary planets, they're amazingly common. And when you see these systems, you see 2 stars in the middle which are orbiting each other and eclipsing. Then you see a system of not just 1, 2, but 3 planets which are all transiting. So the alignment is spectacular. It really is amazing seeing these systems and seeing how common they are. And so the fact that they are as common they are means that we do need to think about the habitable zones of these kinds of planets. So I wanted to finish with telling you that I do have a website where I try to keep track of all this stuff as best I can. It's a website called the Habitable Zone Gallery, hzgallery.org, always been updated, and it has plots of the habitable zone. So if you want to see which planets are in the habitable zone, which are not, I don't make any claims about any of them being habitable, of course, but it is interesting to be used as a target selection tool in the years ahead. So that's all I wanted to say for now. Thank you very much.
Okay, if you have a question for Stephen, put your hand up and I'll get around to you. I see there's a couple of, there's an exoplanet binary over there, I see. I'll get around to you. So Stephen, first question. Before JWST comes along, are there any other missions that we should be looking forward to tie down some habitable zone misconceptions and measurements that might be helping us?
I don't think so. When I was talking about us scooping the discoveries of decades from now, I really did actually kind of mean decades from now. JWST is going to help a lot. And I know that there are people like Sarah Seeger who are working on what we can do with JWST, but in a lot of those cases, those are going to, getting the signal to noise is going to be limited to atmospheres of super-Earths around our very brightest stars. In other words, discoveries from TESS, probably. And so that will be fairly limited in the short term. Longer term, it's important to understand that there are milestones along the way. And each milestone is going to be incremental. That may be frustrating, but that's the way it's going to pan out. And so at the moment, the milestone is target selection. A decade from now, a next milestone met will be with JWST and detecting what do the atmospheres look like for super-Earths, which are kind of at the closer end of the habitable zone, because those are the ones that will be detected with TESS. And then years after that, we're looking at things like some version of terrestrial planet finder and so on. But it's going to be incremental.
For your, actually I have 2 questions. First one is for the eta sub Venus calculations, what cuts did you use for the semi-major axis and planet size? And
I'm sorry, what was
Mic on? Yeah, it is on. Just hold it right up against it.
Hello? Okay. So, first question is for eta sub Venus, 30% or whatever it was. What cuts or bins did you use for semi-major axis size and planet size?
Right. So let's see if I can go back to that plot. Here we go. So what we used for the size of the planets, we're including everything between about everything up to about 1.8.
And down to?
And I'm sorry?
And down to what size?
down to as low as exists in our sample, which you can see here on the plot.
So is that 0.5?
No, actually, that's more like about 0.7.
Okay. And semi-major axis?
Semi-major axis, what we were doing is we were defining it in terms of incident flux. And the incident flux for the outer boundary is the runaway greenhouse, which is around about 2 times the solar constant. The inner edge, which we were using, we calculated that based on atmospheric erosion, and that turned out to be around about 25 times the solar constant. So that was the range that we used.
And quick second question, have you considered the possibility that Tatooine is not a circumbinary, one large star and one small star, far away, chance alignment in the sky?
Oh, you were one of the people who emailed me, weren't you?
I beg your pardon.
I had not. There you go.
Yeah, speaking of Tatooine, do you think of TESS as a successor to Kepler?
Not really. TESS is, I consider the samples of TESS and Kepler to be sufficiently different that it's almost an entirely different experiment. TESS is looking at the entire sky, but the reason for that, of course, is so that you can do all the brightest stars. And it's sampling, from what I remember, from plots which show the sensitivity to different orbital periods as a function of location in the sky. Most of the sky, it's going to go out to about 30-day orbital periods, some parts 60 days, up near the poles, 90 days. And so that sample is going to consist of and plus the photometry, as I understand it, I could be wrong on this, but I think it's not quite as good as Kepler. So it's going to be finding slightly larger planets significantly closer in than Kepler, but they'll be around bright stars. And so TESS will be able to provide the targets for JWST in a way in which Kepler really can't. And that's really the main difference between the two.
So it's a shame about Tatooine because, as we all know, that's the only scientifically inaccurate part of Star Wars. My question is about Kepler. You know, the primary mission's been over for a while, but I know people are still crunching the data. How many more planets, if any, can we expect to pop up from that original data set in the coming months?
Well, I'm not really the person to answer that question. I think I don't want to put Jason Rowe on the spot, but I will, because he can probably give a far more accurate answer.
Sure. So 2 years of data, there's about 3,000 planetary candidates. With 3 years of data, we're approaching around 4,000, and there's probably going to be another couple hundred add on that beyond that. So thousands, and we're just going to keep going as long as we can.
And more of those will be in the habitable zone, right? The longer orbit period.
Well, for G stars, you don't touch the habitable zone until you get 3 years of data. So we've just touched that tip of the iceberg, literally.
Yeah, so I guess the point is that the additional data extends the baseline, so you're finding the longer orbital period planets, right?
I'm wondering if you've looked at circumbinary habitable zones when the two stars are much further apart from each other than the planet closest, than the planet is to the closest star.
Yeah, so that's a really interesting case, especially as you increase the distance between the stars, you're more likely that the stars will be in an eccentric orbit around each other, and so you'll have times when the stars will be quite close, other times when they're further away, and then if you have one planet around one star, what does that mean? Does that mean that the additional star will sometimes push its own habitable zone into yours? And there have been at least 2 papers, I think, at this point that have looked at that. We don't know many examples of that yet. There's the case of Alpha Centauri BB, of course, which is a 1 Earth mass planet in a 2-day orbit This is another case where I'd have to point out to the press that it's not habitable. It's not habitable. But we don't know of too many cases yet of planets in situations where it's the S-type rather than the P-type orbit.
Okay, if there's no further questions, I'll encourage you to come and speak to Stephen afterwards if you want to talk to him about Star Wars and Star Trek and also Tatooine. Stephen, we have this slightly appropriate SETI.org/talks mug for you. It's got a couple of people who've found their way to a habitable zone somewhere, so please enjoy it wisely at a habitable zone near you.
Thank you. Thank you very much, everyone.